Let's start. Just hold on a moment. Okay, so I think everything is all right. Let's start. So we'll start with the trigonometric formula, which is generally used in various physics problems. So let's start with that. Two sine A cos B sine of A plus B plus sine of A minus B. Okay. Two cos A cos B cos of A plus B plus cos of A minus B, 2 sin A sin B. What is the formula for it? Cos of A minus B minus cos of A plus B. Another sets of formula, sin C plus sin D, 2 sin C plus D by 2 cos C minus D by 2. Sin C minus sin D, 2 cos C plus D by 2 sin C minus D by 2. Cos C plus cos D, 2 cos C plus D by 2 cos C minus D by 2. The last one, 2 sin cos C minus cos D is equals to 2 sin C plus D by 2 and sin D minus C by 2. So these formulas are used very frequently whenever you solve any problem. This session will be quite long, guys, so have some patience. Okay, let us now give you some of the important values. Frequently used important values. I hope the audio is clear. Let me just check it. Important values. I hope the audio is okay. Let's start. this is E, so mathematical E 2.718. okay, ln 10, it has a value 2.303. Some other frequently used values are root 2. The value of root 2 is 1.414, root 3 1.732. ln 2 you frequently use 0.693, then 1 upon 4 pi epsilon naught. This value already you always use 9 into 10 to the 9. This volt equivalent of temperature kT by E 0.026 volt, or you can write it as 26 millivolt. Okay, this is at 300 K. Kelvin, room temperature. Let's go for the value of H cut. 1.055 10 to the power minus 34 joule second. Lambda, it has a formula 12400 divided by Eg. This is utilized in the semiconductor physics to find the wavelength corresponding to the band gap. You will get it at angstrom. This is related to the Zeeman splitting, EB by 4 pi MC, although we will separately talk about it in Zeeman effect, but it is very frequently used. EB by 4 pi MC, it has a value 46.7 multiplied by the magnetic field, it is in meter inverse. Okay, let's go for the value of Kb, Boltzmann constant, 1.38 10 to the power minus 23 joule per Kelvin, and in electron volt we can write it as 8.625. This electron volt value is many times used, 10 to the power minus 5 electron volt Kelvin inverse. The product H cut C, let's write it here. This is also frequently used. The value of it is 199 mega electron volt femtometer. This is used in nuclear physics, particle physics. We have Bohr magneton mu b. This is 9.274 10 to the power minus 24 joule per Tesla, or joule Tesla inverse. And a similar unit is there, nuclear magneton, which has a value mu b by 1836. Okay, one atomic mass unit 1.67 10 to the power minus 27 kilogram. This is related to wave number nu bar, 10 to the power 7 divided by lambda. If you express lambda in terms of nanometer, you will get it in terms of centimeter inverse. Okay, here you can write 1U. This is 931.5 MeV per c square. Okay, let's write the gravitational constant G. 6.67 10 to the power minus 11 Newton meter square kg to the power minus 2. R, Rydberg constant 1.097 into 10 to the power 7 meter inverse. Avogadro's number 6.023 10 to the power 23 per mole. Permittivity of free space epsilon naught 8.854 10 to the power minus 12. Okay, the value of permeability in free space mu naught (4 pi into 10 to the power minus 7 Henry per meter. So molar gas constant R 8.314 joule per Kelvin per mole. So let's specify this, because R we have already used. This is R infinity, let's say. Considering the nuclear mass to be infinitely heavy, we have the Rydberg constant, and this is the molar gas constant. Okay. Another unit is there for pressure, 1 atm, atmospheric pressure, 1.01 into 10 to the power 5 Pascal. Okay, these are some of the frequently used important values. I think this is enough. If you remember, you can add few other important values from your side if you want, but this is okay. Let's talk about some of the derivatives which is used generally. Look, this is mathematical methods, so we are basically giving you the basic mathematical formula which are generally used in solving physics problems. ddx of sin inverse x 1 by root over 1 minus x square, ddx of cos inverse x. These are very fundamental level formula, but when you start solving questions, these things are quite used. Okay, ddx of tan inverse x, this formula is used many times, 1 upon 1 plus x square, ddx of cot inverse x minus 1 upon 1 plus x square. ddx of sec inverse x 1 upon x times x square minus 1. ddx of cosec inverse x minus 1 upon x times x square minus 1. Okay, now there are some formula related to hyperbolic. Cos hyperbolic square x minus sin hyperbolic square x equals to 1. This is a little different to our conventional sin square x plus cos square x equals to 1. This is the one. sec hyperbolic square x plus tan hyperbolic square x, this is equals to 1. Cot hyperbolic square x minus cosec hyperbolic square x equals to 1. Okay, here some limits formulas are there. Limit theta tends to 0. I am not giving you all, I am only giving you those formula which are generally used in physics problems. You must have used this formula whenever you have solved the previous year problems. Limit theta tends to 0, sin k theta by theta, this is equals to k. Here little unrelated, but e to the power ln x to the power u, this is equals to x to the power u. Okay. Few trigonometric formulas were left. We should have written it at that place, but that's okay. Let's write little those formula, remaining formula. Okay, sine of a plus b, sine a cos b cos sine b, sine of a minus b, sine a cos b minus cos a sine b, cos of a plus b, cos a cos b minus sine a sine b. These four formula are generally more used. Cos of a minus b, cos a cos b plus sine a sine b. Okay, let's go for some integration formula. This is widely used. Integration of tan x dx, this is log of mod sec x plus c, let's include integration cot x dx. What is the formula? Log of sin x. Okay, few more formula we have. Integration dx by x square plus a square, 1 by a tan inverse x by a plus c dx by x square minus a square, 1 by 2a log of mod x minus a by x plus a plus c. Remember, mod of x is greater than a. Integration dx by root over x square plus minus a square log of x plus root over x square plus minus a square plus c dx by, if you have a square minus x square, then it will be sine inverse x by a plus c. Few relatedly more important formula which you can directly use. 0 to pi sine cube theta d theta. You can evaluate it, but if you remember, that will help you in calculation. 4/3 minus infinity plus infinity to the power minus ax square dx root over pi by a. Here there is a very important formula, minus infinity plus infinity e to the power minus x square x to the power n dx. This is equals to, so if n is odd, then it will be 0, and if n is even and greater than 2, then we will have this formula 1 into 3 into 5. It will go on up to n minus 1 root over pi by 2 to the power n a to the power n plus 1. This is when n is greater equals to 2 and even, and it is 0 if n is greater equals to 1 and odd. So this formula is used many times. Let's move on to the next page. Okay, in this formula we have 0 to infinity e to the power minus alpha x x to the power n dx. I hope you have used it many times. N factorial divided by alpha to the power n plus 1. 0 to infinity to the power minus alpha x. We have x to the power half. Then we have a special formula. You don't need to remember this. So for the sake of completeness, we are giving you this formula. Okay, let's do a little bit of complex thing. Let's start with de Moivre's theorem. Cos x plus I sin x whole to the power n is equals to cos nx plus I sin nx. Few very important formula are there for complex thing. Sin ix, we can convert it into hyperbolic function by using this formula I sin hyperbolic x. Similarly for cos ix, it is only cos hyperbolic x. Tan ix, I tan hyperbolic x. So for sin ix and tan ix, it is a similar formula, but for cos ix, it is only cos hyperbolic x. Okay, now this is cos is a very important function. It can be expressed in terms of the exponentials e to the power ix e to the power minus ix divided by 2, and you can also expand it in infinite series. 1 minus x square by 2 factorial x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial. So even terms, even powers of x with alternate signs. Let's go for sin x e to the power ix. There will be a minus here, and in the denominator there will be 2i. this is equals to x minus x cube by 3 factorial odd powers of x and with alternative sign. Tan x can also be expanded in an infinite series. X plus x cube by 3, 2 by 15, x to the power 5 and so on. You can only remember the first 3 terms. Tan hyperbolic x, the odd term sign will be minus. Okay, alternate x minus x cube by 3, 2 by 15 x to the power 5, then minus terms will come. What is left? Cos hyperbolic x, let's say. Cos hyperbolic x is 1 plus x square by 2 factorial x to the power 4 by 4 factorial. You can easily remember these infinite expansions. We have sin hyperbolic x, x for cos hyperbolic x and sin hyperbolic x, all the terms are positive. Now is the turn for tan inverse x. X minus x cube by 3. There is no factorial in the denominator. Look, these series are quite similar, but you need to remember the unique features. There are two formula for log of 1 plus x minus x square by 2, x cube by 3, log of 1 minus x. All the terms are negative. Minus x square by 2, minus x cube by 3, minus x to the power 4 by 4, and so on. Now there are some special series which we need to talk about. One upon 1 square. Look, the sum of natural number square you know, but if you take the reciprocal and take the sum, 1 by 1 square plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square and so on. This sum will be quite simple, pi square by 6. 1 by 1 square plus, if you only take the even terms, here 2 to the power 0, 2 to the power 2, 2 to the power 4, 2 to the power 6 and so on. This will give you 4 by 3. Now if you take only the odd terms, 1 plus 1 by 3 square, 1 by 5 square, 1 by 7 square. You don't need to remember this. If you can, you remember. I myself cannot remember this thing. But if you remember these things, then it helps you in calculation. Another one is there, 1 minus, if this sum signs are changed, 1 by 2 square plus 1 by 3 square minus 1 by 4 square and so on. This will be pi square by 12. Okay, this is pretty much about this. Now let's talk about some infinite series. Binomial expansion, 1 plus x to the power minus 1 minus n, 1 minus nx plus n into n plus 1 divided by 2 factorial x square minus n into n plus 1 n plus 2 divided by 3 factorial x cube, and it will go on. This is the first formula, 1 plus x to the power minus n, binomial expansion, x is less than 1. Okay, you remember this. I am not writing, but this is quite obvious. When all the symbols are negative, 1 minus x to the power minus n. In this case, all the terms will come positive in the expansion. 1 plus nx, n into n plus 1 by 2 factorial x square, n into n plus 1, n plus 2 by 3 factorial x cube, and so on. Okay, if you take the value of n to be 1 minus x inverse, this is generally used, 1 plus x square x cube and so on, all the terms are positive. 1 plus x, if you do 1 minus x, actually these formulae are coming from the previous two formula, okay, by putting n equals to 1. 1 minus x plus x square minus x cube plus dot dot dot. If you put n is equals to 2, 1 plus x to the power minus 2, what do you expect? 1 minus 2x plus 3x square minus 4x cube and so on. 1 minus x to the power minus 2. When everything is negative, all the term on the right hand side will come positive. 1 plus 2x plus 3x square plus 4x cube and so on. Okay. Now there are some progression, arithmetic progression and geometric progression, harmonic progression is also there. So let's start, which is very much used, arithmetic progression. In arithmetic progression, you know, the numbers increases by some fixed interval, and in the series the nth term is a is the first term plus n minus 1 into d. This d is the common interval. If you calculate sum of n terms, you get the formula. Two formulas are there, n by 2 a plus l. A is the first term, l is the last term. So if you use this formula to find out l, you get an equivalent formula, n by 2 2a plus n minus 1 into d. Okay, let's go for geometric progression. For geometric progression, what is the nth term? Let's say we denote it by Tn, a r to the power n minus 1. this r is the common ratio, and sum of n terms Sn. It can be expressed by two formulae as per the requirement: a into 1 minus r to the power n divided by 1 minus r. This is one formula, or you can take minus common, r to the power n minus 1 divided by r minus 1, depending on whether r is less than 1 or greater than 1. You can use this formula as per your convenience. Now there is a relation between these two. If let us say x be the geometrical mean of A and B, then AB is equals to x square. Using this term, we can get the infinite series of natural numbers. Not infinite, maybe for the first n terms. If you consider sum of n natural numbers. Okay, instead of writing this, let's write it in this way. One plus 2 plus 3 plus 4 plus up to n number. This will be n into n plus 1 by 2. If you take square and take the sum, first n terms square, formula will be n into n plus 1 to n plus 1 divided by 6. If you take the cube of these natural numbers, 1 cube, 2 cube, 3 cube, 4 cube, up to n number of terms, it is like the sum of n numbers square. So n into n plus 1 by 2 whole square. Okay, let's do now a little bit of geometry which is generally used. Let's go with circle. If you have a circle, let's say circle like this, it will have an origin and have some radius. Let's say if this radius is a and the coordinate of the origin, the center, relates alpha beta, then how can you write the equation? Equation of the circle: x minus alpha square plus y minus beta whole square, this is equals to a square. If the radius becomes unit, then it will be 1 on the right hand side. There is another general equation of circle. X square plus y square plus 2gx plus 2fy plus c is equals to 0. For this general equation of circle, what we need? We need the center and the radius. So what is the center? Center is minus g minus f. So if you are given any circle equation, you have to express it in this form, and from there minus g minus f will be the center and the radius will be It is lagging. Root over g square plus f square minus c. Okay, this is for circle. Let's go for parabola. It has a good importance. Remember one thing, the mouth is open in the axis direction where the power is 1. Note first, this will help you to draw the parabola. The mouth is open in the axis direction where the power is 1. So keeping this in mind, let's try to draw. First parabola we will be drawing y square is equals to 4ax. If this is y axis, this is x axis. Y square is equals to 4ax means the power of x is 1, so it will be opening along the x direction. So this is y square 4ax. The mouth is open in the axis direction where the power is 1. Here power of x is 1, power of y is 2, so it is open in the along the x direction. Now let's consider some general parabola equation. What if you are asked to draw a parabola like x is equals to, let's say x is equals to ay square plus by plus c. So actually I should say the maximum power. Okay, na? The mouth is open in the axis direction where the maximum power is 1. So here maximum power of x is 1. So again it will open along the x direction, but here you see there is some offset. So instead of passing through this origin, touching the origin, it will be like this. Okay, it is again opened along the x direction. Let's draw another, then you will understand. Now you are asked to draw a parabola of this form. Let's say it is y is equals to px square plus qx plus c. Here the maximum 1 power is for y, so it will be opened along y direction. There is some offset with the x, so it will be like this. The mouth is now open along the y direction because the maximum power of y is 1 here. So in this way we can draw different parabola. I think you will not be confused. Y square is equals to 4x. If it is x square is equals to 4y, then it will be along this. Okay, one last we can draw for this parabola thing. Let's say this is y, this is x. So if I draw it like this, this is y square. Okay, it was y square equals to 4x, so we have to draw it like this, x square equals to 4ay. The maximum power, the maximum power of y is here 1, so it is opened along the y direction. Okay, so we have circle, parabola, then we'll go for ellipse. Firstly, the equation of ellipse, x square by a square plus y square by b square equals to 1. Here we can consider that a square is greater than b square. Another thing we read for ellipse, eccentricity. Eccentricity gives you a measure like how much a particular conic section is deviated from the perfect circle. E is equals to root over 1 minus b square by a square. Sufficient for ellipse. Let's go for hyperbola. Equation, x square by a square minus y square by b square equals to 1. A square is greater than b square. For this eccentricity, E is equals to, only and positive sign will come, 1 plus b square by a square. The eccentricity of ellipse lies between 0 to 1, right? And it is, you can see from it here, eccentricity is always greater than 1. Like if you understand and read things, then you don't need to remember many things. You can use your own logic, and you can, like many times we forget that there will be a plus sign or a minus sign, but if you know the basic thing, you will not get confused. Okay, otherwise you will get confused at every steps. A very important formula is there, number of diagonals of a polygon. Of sides n into n minus 3 by 2. This one you need to remember. Acha, if you have a little bit of space, we can add a very important relation here. Okay, let's add here minus infinity to plus infinity e to the power minus ax square plus bx dx. This is very widely used in Fourier series, so Fourier transform. Root over pi by a e to the power b square by 4a. There is no negative sign. Root over pi by a e to the power b square by 4a. Chalo. There is an infinite series, let's say Sn. There are a number of terms, u1, u2, u3 and so on, let's say up to un. How can you determine whether this series is converging or diverging? So this series will converge as n tends to infinity, means if you are taking infinite number of terms. At what condition? If you find that limit n tends to infinity, un plus 1. So un plus 1 is what? The n plus 1th term. Un is what? Un is the nth term. And if you take the ratio at a very high limit of n, if it is less than 1, then you can say it is converging, otherwise it is diverging. Okay, let's give you some important formula related to gamma function. This is a very important function for physics aspirants. First of all, it is defined in this way: gamma n 0 to infinity e to the power minus x to the power n minus 1 into dx. Note n is greater than 0. It has some standard value. Gamma 1, it has a value of 1. Gamma half, it has a value of root over pi. This is quite wisely used. If you calculate gamma n plus 1, it gives you n gamma n, and this is also equals to n factorial. If let us say gamma m times gamma n equals to 1, then we can write m plus n equals to 1. Okay, so these were some general formula. Now we are actually starting our mathematical method. So we will start with vector. Some of the very important vector formula: divergence of phi a, where phi is some scalar, a is a vector. This formula I think you have used many times. Grad phi dot a plus phi times divergence of a. Curl of phi a grad phi cross a plus phi time curl of a. This is divergence of grad phi, grad square phi. Now there are two very important things: the curl of a gradient. The curl of the gradient of phi is 0. Curl of the gradient is 0, and the divergence of the curl of a, this is a vector function, it is also 0. Okay. Let us go for the vector triple product formula. A cross B cross C, B into A dot C minus C into A dot B. Del R to the power n this will be a vector n r to the power n minus 2 vector r. Let's say we have a surface like this. It is given by phi of xyg, this is equals to c. Now if you draw a normal at this point, at any point, this is phi, this will be your grad phi. Now any unit vector along this perpendicular direction will be given by n cap. So this is the direction of n cap, let's say grad phi, and this point is, let's say, xyz, any point. This will be grad phi at xyz. You must have seen many formula, many question on based on this. I am not writing the words too much to make it as precise as possible. If F is a conservative field, then you can write or express F as gradient of some scalar minus grad phi. And if you are asked to check whether the field is conservative or not, you have to check the curl. If the curl is 0, it is conservative. If it is not, then it is not conservative. Now there are two very important vector related theorem. One is Gauss divergence theorem, which is given by this, to actually transform the divergence or the volume integral to a surface integral. Another important theorem, Stokes theorem. This is quite widely used, Stokes theorem. What is there in Stokes theorem? It converts the line integral into a surface integral. Divergence theorem converts volume integral into a surface integral. Stokes theorem converts a line integral to a surface integral. Okay, this is related a little bit unrelated, but we should know it. Let's say if you have a periodic function f of x, it has a period, let's say p. Then if you have another function, let's say ax plus b, so a scalar a has been multiplied with the variable, then that function will have a period p by modulus of a. So actually the period is getting divided by the scalar factor with modulus. Period cannot be negative, that is why. Okay, so vector is over. I think this many formula are okay for vector. Let's go for the Fourier series. So using Fourier series you can expand any non-sinusoidal function in terms of the sinusoidal function. The general expression a naught by 2 n equals to 1 to infinity n cos nx n equals to 1 to infinity bn sin nx. Where you can write a naught as 1 by pi minus infinity to plus infinity f of x dx. An you can write 1 by pi minus infinity to plus infinity f of x cos nx dx. Bn you can write 1 by pi minus infinity to plus infinity fx sin nx dx. Here we need to remember that this fx, it has a period of 2 pi. Okay, the interval may be from 0 to 2 pi or minus pi to pi. Okay, so remember this one thing, coefficient of integration. Here it is 1 by pi, 1 by pi, 1 by pi. It is 2 upon interval. Interval is 2 pi, so 2 by 2 pi, so 1 by pi. Now let's go for another thing. Let's say fx now has a period, instead of 2 pi it has a period, let's say 2l. Then we can expand the function in Fourier series in this way: a naught by 2 plus n is equals to 1 to infinity n cos n pi x by l Hello Abhijit. बताओ. So for that case, if fx has a period of 12, then the formula will be converted into this, and you can easily find out the coefficients. Here see, as I told you, it is 2 by interval, so interval is 12 here, so 2 by 12 is 1 by l, so every time you will use 1 by l. And you can remember only one formula and the rest of the formula will come out automatically. I think the second one you can remember, which one I am writing currently. Look, here we are considering it is minus L to L, it can be 0 to 2L, so you have to just copy paste the given limit in your question. Okay. Now one thing I think you must have noticed here, look, here what I am writing, cos n pi x by l. So I am not writing cos of sine, I am just writing n pi x by l. For this 2 pi period, what is L? L is pi, right? It is either from minus L to L, minus pi to pi, or 0 to 2 pi, 0 to 2L. So n pi x by L is like pi, so that is why it is nx. That is why in this formula you have nx. Okay. So whatever formula you will be given, you can just compare and you can write it and convert as per your convenience. So these are the two things. Another Fourier series is there for complex. Let's go for that. complex Fourier series f of x, this is equals to k is equals to minus infinity to plus infinity ck e to the power I kx, where this coefficient ck is 1 upon 2 pi 0 to 2 pi f of x e to the power, here it was plus ikx, here it will be minus ikx dx. This is when f of x has a period of 2 pi. Now the same, if you consider for a period of let us say 2l, then you can write it Cn e to the power I n pi x by L, where the coefficient Cn is given by this 1 upon 2l minus L to plus L f of x e to the power minus I n pi x by L dx. For this case, your f of x has a period of 12. This n can be 0, plus minus 1, plus minus 2, and so on. Now you are given a function and you are asked to find out the average value. Average value of a function over an interval, let us say a varying function you are given over some interval of a b, and you are asked to calculate what is the average. So you will be using this formula, average of f of x. It is also sometimes written as fx with a bar symbol, 1 by upper limit minus lower limit integration a to b fx. This is a very general formula, we can use it at many places. Okay, there is a very important theorem in Fourier series, Parseval's theorem. We have a function f of x, if you take square and then take the average, then the formula as per the Parseval's theorem, it will be a0 square plus half times n equals to 1 to infinity an square plus bn square. Now if the function is even or odd, then depending on that a0 may be 0, an may be 0, and bn may be 0. Okay, and the formula will be modified accordingly. Okay, if we have some space for vector, I think we should leave some space after every formula. Okay, anyways. Two additional formula for vector, condition for coplanarity. Of vectors means two, three vectors are lying on the same plane. Let us say for three vectors a, b, c, if you have to find out a condition so that all the three vectors are lying on a same plane, then the necessary condition will be a dot b cross c, this should be equals to 0. Then you can say a, b, c are coplanar vectors. And now very important thing is there, let us say we have a vector a. If you want to find out the component of a along any direction, let us say n cap, what you write? A dot n cap, right? Now instead of this, if you are given a vector like this A, and you have to find out the component along some other vector B, then we call it projection of A on B is A dot, we took n cap is the unit vector along this, so here also you have to take the unit vector along this direction is B cap. What is B cap? Vector B by modulus of that vector. Okay, let's start differential equation. Linear differential equation, first order. Dy dx plus p of x into y q of x. So if you have this q of x is equals to 0, then the equation is homogeneous. If it is non-zero, then it is non-homogeneous. To solve this kind of differential equation, you need to find out the integrating factor, which is given by this formula, e to the power integration p of x dx. P of x is the coefficient of y. Now the solution will take this form: integrating factor multiplied by a is equals to integrating factor into q, the function which is lying on the right hand side, dx plus c. So you need to keep in mind this form of differential equation and the solution. Okay, here we have Bernoulli's equation. The general form of Bernoulli's equation dy dx, so it is very similar, but on the right hand side we have an extra y to the power n. So for this type of Bernoulli's equation, we need to solve this differential equation, we need to put v is equals to y to the power 1 minus n, and after that this given equation will get converted into this dv by dx plus p into 1 minus n times v is equals to q into 1 minus n. So now we have got back this usual form. Now we know how to solve it. Okay. Let's go for the second order differential equation. What is the standard form? D square y by dx square plus p of x dy dx plus q of x into y r of x. R of x is 0 means homogeneous, non-zero means non-homogeneous. By putting r of x equals to 0, we will get homogeneous differential equation. It is like y double prime plus p of x y prime plus q of x y is equals to 0. This is the homogeneous differential equation. And r of x not equals to 0, this gives us non-homogeneous differential equation. Now the solution for this is given by y is equals to, let's say we are writing y homogeneous, y h of x. For non-homogeneous differential equation, the solution will be written as y sum of the homogeneous part, and another we need to calculate the particular integral. Okay, y h x means if you are given a non-homogeneous differential equation, you have to first find out the solution for the homogeneous part, then you can find out the particular integral, then you will add them. Okay, so to solve the homogeneous part, you need to write the characteristic equation. Okay, characteristic equation, it is like if we consider some operator, let's say I am writing it here, d dx, we can consider it like d square by dx square, like a d square, then it is like d square plus p into d plus q into plus q. In this way you can write. So characteristic equation will be m square plus, let's say, pm plus q equals to 0. This is a quadratic equation. It will give you two roots, m1 and m2. Depending on this m1 and m2, the solution will be different. So there may be we can consider 4 cases depending on the nature of m1 and m2. Let's say case 1, m1 m2 are two distinct real roots, two distinct real roots, m1 and m2. In that case, you can write the homogeneous solution as c1 e to the power m1x plus c2 e to the power m2x. Case 2, when the roots are equal and real, that is, we can write m1 m2 are same, it is equals to, let's say, m. In that case, you can write the homogeneous solution as c1 plus c2x e to the power mx. Case 3, complex conjugate roots. These complex roots will always appear in pairs. Okay, there will not be a single root. If you have a complex root, it must have its complex conjugate. So one root, let's say alpha plus I beta, another root will be alpha minus I beta. In that case, you can write the solution as this: e to the power alpha x c1 cos beta x plus c2 sin beta x. Now, when complex roots are equal, means you have to consider 4 roots. If two imaginary roots be equal, total 4 हो जाएगा. Let's say m1 is equals to m2, this is equals to alpha plus I beta, and m3 m4 alpha minus I beta. This situation doesn't happen. I think case 4 is not necessary, but still for the sake of completeness you can write. Okay, let's remove this case 4. It is not seen actually. Second order differential equation will only get 2 roots. This is not going, guys. So once you evaluate the homogeneous part, you have to tackle the particular integral part. Okay. Particular integral is written in short pi. Look, we have defined d dx is equals to d square by dx square is equals to d square. In a similar manner, if you consider 1 by d, it is like integration of dx. It is like integration symbol. Okay, na? Now for particular integral there may be a few cases again. Let's say case 1, depending on the nature of Rx, we will get a different kind of particular integral. Look, Rx may be some exponential function, some sinusoidal function, some algebraic function, or some other function. So depending on that you will get a few cases. Let's say this R of x is an exponential function. In that case you will calculate the particular integral as 1 upon f of d. Look, what is f of d? Here if you write, let's say d square plus p times d plus q is equals to, let's say, r of x. So this part is written as f of t. So 1 by f of d e to the power ax, you have to put d is equals to a and make sure that f of a is not equals to 0. The denominator should not be 0. By any chance, if the denominator is 0, then you have to use this formula, x times 1 by, you have to take the derivative. Then you have to put d is equals to a, and you have to make sure that f prime of a is not equals to 0. Okay. F of a is equals to 0, but a prime a not equals to 0. It may happen that a prime a is equals to 0, then what you will do? You will use this formula, 1 x square divided by 1 by f double prime of d e to the power x you have to put d is equals to a, and here f prime a is equals to 0, but f double prime of a not equals to 0. Okay, this is case 1. Let's go for the case 2. If Rx is equals to sine of x plus b, or you can also get cos of x plus b. In that case, particular integral will be 1 by f of d square sine x plus b, or cos of x plus b. What you need to do, you need to put d is equals to a, make sure f of a not equals to 0. If somehow this becomes 0, sorry, here we have to put d square is equals to a square. Here we are writing f of d square. Okay, just little bit of improvise. Put d square is equals to minus a square, make sure f of minus a square is not equals to 0. If it becomes 0, then the formula is as usual, you have to multiply by x and you have to take the derivative in the denominator. This is same for both functions, sine and cos. You have to put d square is equals to minus a square, and f of minus a square may be 0, but f prime of minus a square is not equals to 0. It may happen again, this denominator may be 0 again, then in that case you have to write it x square f double prime of d square sine of x plus b or cos of x plus b. And again, as usual, you have to put d square is equals to minus a square, f prime of minus a square, it may be 0, but f double prime of minus a square is not equals to 0. Okay, this was case 2. Let's go for case 3. If the function on the right hand side is some polynomial of x to the power m may be a positive integer, in that case the particular integral will be 1 by f of d x to the power m. So what you have to do, you have to expand f of t in some series. You can use binomial theorem. We have already given you the formula for binomial series. One last case for this one, case 4. If let's say, no, second last, this is if you have a function in this form a to the power x times v of x, in that case you can write the particular integral as 1 by f of d e to the power x into v. This is equals to, you can take the e to the power x to the left, but you have to do it f of d plus a. times p. Another case may arise, fifth case, if Rx is any function of x, then the particular integral will be 1 upon f of d Rx. So what you have to do, you have to resolve f of d into partial fraction. You have done it many times in your class 12, and thereafter you have to operate each function on Rx. R of x. Okay, let us now talk about little bit about the Wronskian. Wronskian, let's say you have a second order differential equation, so you will get two solutions, let's say y1 and y2. So Wronskian of y1 y2 is evaluated or defined in this form: y1 y2, y1 prime, y2 prime. These are the derivatives of y1 and y2. So this is y1 y2 prime minus y2 y1 prime. When we use this Wronskian you can use to check whether the solutions are linearly independent or not. If you find out the Wronskian, if you get 0, then you can say that the solutions are linearly dependent. Linearly dependent. And if you get not equals to 0, then they are linearly independent. Now Wronskian can also be used to evaluate, like let's say if you know only one solution, with the help of Wronskian you can find out the other. So there is a formula, Wronskian, this is equals to c e to the power minus integration p of x dx. So using this formula you can find out the value of Wronskian at different values of x. Okay, Wronskian is equals to c to the power minus integration px dx. What is p? P is the coefficient of dy dx. We have seen it earlier. Okay, another very important differential equation is there, Cauchy-Euler differential equation. So the standard form of Cauchy-Euler differential equation is x square d square y by dx square plus ax dy by dx plus by is equals to 0. So to solve this kind of equation we need to follow a special approach. Okay, just hold on a moment. Okay. So this is the standard form of Cauchy-Euler differential equation. Let us write a little more general form. Let's say the coefficient there, it may not give you only x square, there may be some number also. So let's make it generalized. Let's say this is a2 x square d square by dx square, then a1 x dy dx plus, okay, a2 a1 and the coefficient of y is a0. Let's say a2 a1 and a0. And it may also give you non-homogeneous. So on the right hand side also there may be some function q of x. So first of all you have to identify this Cauchy-Euler differential equation and you have to determine a2 a1 a0. Once you identify, next thing you can let that, let's say x is equals to e to the power z, then your differential equation will get converted into this form: a2 d square y by dx square plus a1 minus a2 dy by dz, sorry, here it will be dz square, no, plus a naught y, this is equals to q of x was there, then now q of z. Now you can solve it conventionally. What was the problem with Cauchy-Euler differential equation? Because of this x square we were not able to solve it, but as we have taken x is equals to the power z, it has come to our original, the usual form of this. That is why we have taken this x equals to the power z. So you can now solve it conventionally. After solving it conventionally, you can write the solution in terms of z, and at the end you just need to replace whatever you have taken e to the power z. So you will get e to the power z, you have to replace e to the power z by x, then it will be done. So you don't need to worry much about this differential equation, you just need to identify a2 a1 a0, and you just need to remember this: a2 d square by dz square plus a1 minus a2 dy dz plus a naught y is equals to q of z, then you are good to go. So I think this is pretty much for the differential equation part. Let's come back again for the complex analysis part. Now in complex analysis, some of those things you need to remember is a 1 we can write it as e to the power twice pi I, minus 1 if you want to write in terms of exponential, you can write it e to the power I pi. Then you need to write I, you can also express it in terms of exponential e to the power I pi by 2. If you need to write minus I, you can write e to the power 3 pi I by 2. Log of, let's say, minus 1, how can you determine the value? So simply minus 1 you replace with e to the power I pi, then this will be I pi. Okay, log of, let's say, I, then log of I we have written as e to the power I pi by 2. Okay, so this will become I pi by 2, In a similar manner, log of minus I you can also express log of e to the power 3 pi I by 2, 3 pi I by 2. Okay, let's say you have a complex function f of z. We can write it as the sum of the real part plus I times the complex part of that function. Now, to check analyticity, we need to check the Cauchy-Riemann condition. What is the Cauchy-Riemann condition? Del u by del x, it should be del v by del y, and del u by del y this should be minus del v by del x. If you are given in polar coordinates, then del u by del r, it should be 1 by r del v by del theta. This is very easy to remember. You see 1 by r, here you have taken 1 by r, so del v by del theta, and let's say del u by del theta, okay, minus r del v by del r. Okay. Try to keep an eye on the limits. Try to keep an eye on the units on both sides. This function f of z, if it satisfies this Cauchy-Riemann condition, then it is said to be analytic. Now, there is another thing called harmonic function. What is an harmonic function? Any function which satisfies the Laplace equation is known as a harmonic function. Okay, so Laplace equation in 2D Cartesian coordinates, this is equals to 0. So u, v both are satisfying the Laplace condition. So they are harmonic functions. U and V are called conjugate harmonic function. Now, a short trick is there to identify whether the function is analytic or not. So, whenever you see in f of z, if you see z, then that gives you an analytic function. If you see z bar x minus iy, then it is non-analytic. hold on a moment. Okay, if instead of if you see z bar means x minus iy, and two other things are there to recognize the non-analytic function. Either you see z bar x minus iy, or if you only see real of z, that is x, imaginary of z, that is y, then in these cases it will be non-analytic function. Okay, an important series is that Taylor series. About z is equals to z0, f of z, f of z0, z minus z0 by 1 factorial f prime of z0, z minus z0 whole square by 2 factorial f double prime of z0, and so on. Okay, let's go for radius of convergence. It is given by this formula, let's say r, limit n tends to infinity, n by n plus 1 for any infinite series. Okay, we have done Taylor series. Let's go for Lorentz series. Lorentz series expansion, and you express it in this way: a naught plus a1 z minus z0 a2 z minus z0 whole square, then the negative powers b1 by z minus z0, b2 by z minus z0 whole square, and so on. So we can write it in a shorthand notation: n is equals to 0 to infinity an z minus z0 whole to the power n, and let's say n prime is equals to 1 to infinity bn prime z minus z0 whole to the power n prime. This coefficient of b1 is the residue for z is equals to z0. Now, depending on the how many terms survives, we will get different poles. Let's say n prime tends to infinity, means infinite number of terms are non-zero, then we can say that at z equals to z0 we have essential singularity. Okay, let's say this series truncated or ends at some finite terms of n prime, then that is non-essential singularity. Let's say some term 4, then we will call it pole of order 4. Z is equals to Z0 is a pole of order 4, and if n prime is 1, only one term survives, then we can say it is a simple pole, pole of order 1 or simple pole. And all of these poles are evaluated at Z equals to Z0. Now what is the value of an and bn? An, you can express it like this, 1 upon, although you don't need to remember this, but for the sake of arguments, f of z dz by okay. Now what is this C1 and C2? So if we have a function which is analytic in the annular region between two circles, let's draw the circles. Okay, so you have a scenario like this, z is equals to z0 and the function is analytic in this annular region. Let's say the radius are r1 and r2. The outer one is C1 and the inner one is C2. So for this case we can write all these things. Now as I told you, B1 is the residue for Z equals to Z0. So if you calculate B1 prime, because we have denoted it by prime, how can we write? So you can use this formula, 1 by 2 pi I integration over C2 f of z dz. N equals to, if you put n equals to, sorry, here it will be n prime, right? N prime is equals to 1, then this will be 1, the denominator will be 1, and you will get f of z dx dz. So this formula you can also use to evaluate the residue. This is the residue of f of z at the pole z equals to z0. So this is one way you can find out the residue. There are some other methods to calculate the residue. So we will continue it from here. Let's take a small gap, maybe 15-20 minutes, then we will start again from here. So simple pole at z is equals to z0, then you can use this formula, residue at z is equals to z0 is equals to limit z tends to z0, z minus z0 multiplied by f of z. Okay, this is the first formula. Second formula, residue at any pole of order, let's say m. In that case, the formula will be residue. You need to remember this formula, okay? 1 by m minus 1 factorial limit z tends to z0 d m minus 1 dz m minus 1 multiplied by z minus z0 whole to the power m f of z. Okay, this is the second formula. Now if you are given a function in this form, which can be written as the ratio of phi of z and psi of z, and where this psi at the pole psi at z equals to z0 is equals to 0, but the numerator is phi at z0 is not equals to 0. In this case, what you can write, the residue at z is equals to z0 you can write it in this way, limit z tends to z0 phi of z divided by psi prime of z. Okay. Fourth formula, we have residue, let's say at infinity. The residue, if we calculate residue at infinity, then formula will be limit z tends to infinity minus z times f of z. And once you know the residue, we can easily use the Cauchy's residue theorem to evaluate the integral. Cauchy's residue theorem, the general formula is integration of fz dz evaluated over some contour C 2 pi I into sum of residues. Not all residues needs to be considered, only those residues which are lying inside the curve C. Residues at the poles within C. Now in this context, we have two sub formula. It depends upon the contour direction. Let's say if you have a contour like this, if the contour is traversed in the clockwise direction, then there will be a little bit change in the formula. This is clockwise contour. The formula will be changed to, there will be a minus sign, minus 2 pi I into sum of residue, and this formula is for a contour which is considered anti-clockwise. Okay. Now if there are some poles which is lying on the real axis, then we can write it. The formula will become for poles lying on the real axis. then the formula will become, this 2 will be removed, only pi I into sum of residues. Sum of R means sum of residues at the poles. Okay. A very important thing is there, which is known as Jordan's lemma. So let's talk about this Jordan's lemma. In Jordan's lemma, we consider a semicircular arc like this. Let's call this arc tau. Okay, and this radius is r minus r to, let's say, plus r. So let, this is not used so much, you can directly use this in solving problems, but let's write this Jordan lemma. Let f of z is less equals to m by r to the power k for z is equals to r e to the power I theta, where this k is greater than 0, m is also greater than 0, and they are constants. Then as per Jordan's lemma, what you can write? Limit r tends to infinity. If you consider r tends to infinity, this semicircular arc will cover the whole space on the upper side of the x-axis. So integration evaluated along this semicircular arc, e to the power I m z f of z dz will be equals to 0. So we directly utilize this result of Jordan's lemma when we solve some complex integration problem. Remember, here tau is a semicircular arc of radius r in the upper half plane of x-axis, and m is a positive constant. Okay, this is Jordan's lemma. Now let me just give you some of the very important integration on this complex analysis. Sometimes you may be asked to solve some integration, some real variable integration. You can use complex analysis to solve them. So minus infinity to plus infinity dx by x to the power 4 plus 1, this will be pi upon root 2, minus infinity plus infinity dx by x to the power 6 plus 1. You can solve it by using complex analysis, but if you remember the results, it will be good for 2 pi by 3. So if you evaluate 0 to infinity, then it will be pi by 3. Okay, minus infinity plus infinity sin mx by x dx, this is equals to pi, and on the other hand cos mx by x dx is equals to 0. Few other integrations are there, minus infinity plus infinity e to the power ax by e to the power x plus 1 dx, pi by sin a pi, then we have minus infinity plus infinity e to the power minus x square cos 2bx dx, this is equals to root over pi e to the power minus b square. And the same in case of sin 2bx dx, e to the power minus x square sin 2bx dx, this will be 0. Two more formula. minus infinity plus infinity cos x square dx. This is equals to root over pi by 2. If you go for 0 to infinity, then it will be half into root pi by 2. Then minus infinity plus infinity, if you calculate sin x square, these are very special problem, so you can remember the result, root over pi by 2. Another thing is left for complex analysis, branch cut and branch point. So let me give you those formula for branch cut and branch point. Then the complex analysis part will be over. Branch cut and branch point. The formulas you can write. Let's say you have a function log of z minus 0. In this case, 0 is the branch point singularity. Let's say this is f of z, right? F of z in a general log of z minus z0. Then you can say that z0 is a branch point singularity. If you are given a function like this, z to the power a, z minus z0 to the power b, then you see z is equals to 0 is a branch point, if and only if a is non-integer. Okay, so it is like z to the power a is like z minus 0 whole to the power a. Here z minus z0, so z0 when it will be a branch point, z equals to z0 is a branch point, if and only if b is non-integer. And finally, if you consider z is equals to infinity, then z is equals to infinity is a branch point, if and only if the sum a plus b is non-integer. If you are given a problem based on this branch cut and branch point, you can directly utilize this formula. Let's say 0 to infinity x to the power alpha f of x dx. So the formula will be 2 pi I divided by 1 minus e to the power 2 pi I multiplied by alpha into sum of residue for z to the power alpha f of z, and as you know this alpha belongs to 0 to 1. You have to calculate the residue except at the origin. Okay, note, poles are to be determined from f of z, not this combined function, only f of z. Let's go for some formula for matrix. You know, So matrix rotation operator. The following rotation matrices operator rotates by an angle theta in 3D. So if you have Rx, so it will rotate about the x axis, Rx of theta, the matrix rotation operator matrix 1 0 0 0 cos theta minus sin theta 0 sin theta cos theta. Rotation about y axis is governed by this rotation matrix cos theta 0 sin theta 0 1 0 minus sin theta 0 cos theta. Rz cos theta minus sin theta cos theta 0 0 1. So these three matrices you can remember. Cos theta minus sin theta cos theta. Okay. A transpose equals to A transpose A equals to identity, then we can say A is orthogonal. A inverse A, then A is unitary. A dagger A equals to I, that condition is also there. Idempotent matrix A square equals to A, if you get, then that is called idempotent of the matrix, idempotent matrix. If you want to calculate the inverse of a matrix, then you have to find out the adjoint of that matrix divided by the determinant. This determinant must be not equals to 0 if inverse of A exists. This is a very trivial thing, you already know. Just go for the Cayley-Hamilton theorem. So it has a statement: every square matrix satisfies its own characteristic equation. So as per this, if A0 lambda to the power n a1 lambda to the power n minus 1, a2 lambda to the power n minus 2, and so on. It is the characteristic equation of a square matrix A then a0 a to the power n, an a to the power n minus 1, a2 a to the power n minus 2, and finally an. Look, an is a number, so you have to multiply with the identity matrix to make it a matrix. This will be equals to 0. So this is very important. If you get a condition A transpose equals to A, then A is called symmetric matrix. And if you get A transpose equals to minus A, then you call A to be square-symmetric matrix. If you get A dagger equals to A, then you call A to be Hermitian. And if you get A dagger is equals to minus A, then you call A to be square Hermitian or anti-Hermitian. You know, the eigenvalue of Hermitian matrix are real. And the eigenvalues of the anti-Hermitian matrix are imaginary or 0. There is a very important term called similarity transformation. So if you have two matrices, let's say B and A, and B you can write it in this way: P inverse A P. This operation is known as the similarity transformation, and you say B is similar to A. Now the similarity transform or similar matrices, they possess some of the important properties. First one, they have same determinant. Same trace means the eigenvalues are same actually. A and B have same eigenvalues, but their eigenvectors are not same. Different eigenvectors. Okay, so you can use this similarity transformation in diagonalizing a matrix. So if you want to diagonalize a matrix A, you have to do it in this way: x inverse Ax. So this D matrix is the diagonal form of A. Now x and x inverse, how can you determine? So you have to find out the eigenvalues of A. As the entries on the main diagonal. What about x? X is the matrix with the eigenvectors of A as the column vectors. So you have to find out first the eigenvalues and the corresponding eigenvectors, and if you write the eigenvectors in columns, then the matrix will be X. Now once you find out D, you can do many operations. If you want to find out the power of D, then you just need to go like this. Now in the same way you can go for any functional matrix. Functional matrix will be written in this way: f of A is equals to x times f of D x inverse a very important formula is there: determinant of exponential of A equals to exponential of trace of A. Okay, I'm giving you an example. Let's say we have a matrix A. It is given by 1 0 0 minus 1. Okay, then we can write A to the power n, 1 to the power n, 0 0 minus 1 to the power n. If you want to calculate e to the power a, what you gonna do? You have to do the operation here. E to the power 1 means e, and e to the power minus 1. So the operation will be on the diagonal elements. Okay, let's say sine of A, then sine 1. The off diagonal elements will not get affected, only the diagonal elements will get affected. Okay, so I think this is enough for the matrix part. Let's go for now the Laplace part, Laplace transform. Just hold on a moment. F of t is written as f bar of s. You need to remember this main formula, 0 to infinity e to the power minus st ft dt. Okay, so let me just give you some functions and their Laplace transform. So let us make a table. So on the left hand side we will write the functions of which you want to calculate the Laplace transform and this Laplace transform, functions and the Laplace transform. So Laplace transform of 1, so here the f of t is 1, so Laplace transform of 1 is 1 by s. Laplace transform of t to the power n factorial by s to the power n plus 1. Laplace transform of f of t minus a e to the power minus s f bar s. Laplace transform of e to the power at, this will be 1 by s minus a. You can consider like 1 into e to the power at. Laplace transform of e to the power minus at, then obviously it will be plus a. Laplace transform of sine at, it is a by s square plus a square. When you consider cos at, this will be s by, and when you consider sine hyperbolic, for hyperbolic negative sign will come in the denominator, a by s square minus a square. Laplace transform of, let us say, cos hyperbolic at, so this will be s by negative sign in the denominator, so s square minus a square will come. Okay. Now if you add this, multiply this exponential factor e to the power at, let us say sine bt. So what is the purpose of e to the power a? You see, s, it will make s to s minus a. So a by s square plus a square or sine at, so e to the power at will be, here sine at was there, here it is sine bt, so this will be b by s will become s minus a whole square plus b square. Okay. So we have many more Laplace transform, so we are utilizing this space. Here we have functions, their Laplace transform, functions, their Laplace transform. So we have done it till e to the power at sine bt, e to the power at, let us say cos bt. If we have s minus a, s will be s minus a divided by s minus a whole square plus b square. Now if you do the same for the hyperbolic functions, e to the power at, let us say sine hyperbolic bt, then it will be b by, it is affecting only s part, so s minus a whole square, and for hyperbolic there will be negative sign. Laplace transform of e to the power at cos hyperbolic bt. For this it will be s minus a divided by s minus a whole square minus b square. Okay. Laplace transform of delta function, Dirac delta function t minus a, if you have, it will be e to the power minus as, and Laplace transform of simple one dimensional Dirac delta function will be 1. Laplace transform of, let us say, e to the power at t to the power n. So for t to the power n we have n factorial by s by n plus 1. Then s will be s minus a. Very simple formula, there is nothing difficult here. F of a t 1 by a f bar of s by a. So a general formula e to the power a t f of t f bar of s minus a. This is called the shifting property. Okay. Laplace transform of integral, let's say 0 to t ft dt. This will be f bar of s divided by s. Okay. Few more formula are left. Okay. Laplace transform of t to the power n f of t. This will be minus 1 to the power n nth order derivative with respect to s of f bar s. What is f bar s? F bar s is the Laplace transform of f of t. Another, let's write here, f of t by t. It will be s to infinity f bar s to s. A few more formula. Let's say Laplace transform of linear combinations of some function a into f of t plus b into g of t c into h of t. Then you can just separately take the Laplace transform on each function. Another very important formula, Laplace transform of f to the power n t. This is nth derivative of the function f of t. Okay, so this will be s to the power n f bar s minus s to the power n minus 1 f of 0 minus s to the power n minus 2. So this power of s is decreasing by 1 unit every time, and it was f bar s, then f of 0, then it will be f prime of 0, then minus, all the terms will come minus, and s, the power of s will decrease by 1 unit, and it will be like this, and so on. Now there is a function called unit step function. How does this function look like? Let's say we have a function like this, u t minus a. Okay, so it will have value 0 till t equals to a, and at this point it will take up a value of unity. That's why the name unit step function. So mathematically u of t minus a, it is giving you 0 till a and it is 1 as you cross a. Now Laplace transform of such unit step function is given by e to the power minus as by s. It's a very important formula. Another formula, Laplace transform of f of t minus a, u of t minus a, and this will be e to the power minus as f bar s. Okay. Now let's go for convolution theorem of Laplace transform. What does it say? If the Laplace inverse of two functions, let's say one function f of t, Laplace inverse of f bar s is equals to f of t, and Laplace inverse of some another Laplace transform function, let's say that is g of t. Then if you take the Laplace transform of the product of the Laplace transformed functions, then that will be equals to the convolution of the two functions. What is the formula for convolution? 0 to t f of u g of t minus u du, and this is written in the form of f star g. This is the meaning of convolution of f and g. F star g, this is known as the convolution of f and g. Okay. Now let's quickly review the coordinate systems: line element, area element, and volume element. So spherical, I am not writing any everything, just some brief outnote. Spherical polar coordinates, the formulas are x is equals to r sin theta cos phi, y is equals to r sin theta sin phi, z is equals to r cos theta. Whenever you will write the line element in spherical polar coordinate, you will write dl dr r cap, r d theta theta cap, r sin theta d phi phi cap. The volume element is quite straightforward, you just multiply them, dr r d theta r sin theta d phi, and as you get r square dr sin theta d theta d phi. You know r runs from 0 to infinity, theta runs from 0 to pi, and phi runs from 0 to 2 pi. Now the unit vectors r cap cross theta cap, it will give you phi cap. You can consider a cyclic rotation like this, r theta and phi cap. So if you take the cross product of r and theta, you get phi. Theta and phi gives you r. and phi and r gives you theta. Whenever I use eraser, it lags. Okay. Now there is a transformation rule from Cartesian to spherical. Unit vectors, let's say. So for this you need to consider a table like this. So first of all you will write r cap, theta cap, phi cap, and x cap, y cap, z cap. For a clearer understanding, let's write the transformation rule here. X is equals to r sin theta cos phi, y is equals to r sin theta sin phi, z is equals to r cos theta. So when you calculate x cap dot r cap, so we have to take derivative with respect to r. So what we have left is sin theta cos phi, sin theta cos phi. Then x and theta, then what you have, derivative of sin theta is cos theta, and phi is remaining, x and phi. So r sin theta and cos phi, theta part is neglected, so this will be minus sin phi. Okay, derivative of cos phi is minus sin phi. So in this way you can handle this. Now y and r, so sin theta sin phi, then this will be cos theta sin phi, and this will be cos phi. Z and r, cos theta minus sin theta, and there is no phi term, so this will be 0. Okay, let's move on. Spherical polar coordinates is done. Let's go for the cylindrical polar coordinate. The transformation rule is right. So here the coordinates are r, phi and z. Sometimes it is also written as rho phi z. So x is equals to r cos phi, y is equals to r sin phi, z is equals to z. Lyle element, let's write dl, dr r cap, r d phi, phi cap, dz z cap. Volume element, just product of it, r dr d phi dz. Let's also calculate or write the transformation between the Cartesian and cylindrical polar. So as usual we will write r cap, phi cap and z cap, x cap, y cap and z cap. So x equals to r cos phi. So what we will have here? Cos phi, x and phi. So we'll have minus sin phi, x and z, 0, y r, so sin phi, this will be cos phi, 0, 0, 0, this is 1. Now we need to know the gradient divergence curl in different coordinate system, the expressions for gradient, divergence and curl. So let's go for gradient. I am not writing in Cartesian, you already know about it. For cylindrical we are writing, and for spherical polar. Grad of V del V by del R, r cap 1 by r, del V by del theta, theta cap 1 by r sin theta, del V by del phi, phi cap. So this is in spherical polar. Let's write for cylindrical polar. Del V by del R, r cap 1 by r, del V by del phi, phi cap, del V by del z, z cap. Divergence, let's write for spherical polar. Divergence of A is a vector AR, r cap, A theta, theta cap, A phi, phi cap. For that, divergence of A, we can write it in this way: 1 by r square del del r, r square AR, 1 by r sin theta, del del theta sin theta, A theta, plus 1 by r sin theta, del A phi by del phi. This is the divergence formula in a spherical polar coordinate. For cylindrical polar, look, the vector in cylindrical polar coordinates can be written in this way: AR, r cap, A phi, phi cap, and AZ, z cap. Then we can write the divergence formula: 1 by r square, 1 by r del del r, r AR, 1 by r del A phi by del phi, del AZ by del z. So we have gradient, divergence. Now we'll write curl. Curl in spherical polar coordinate. Curl of A is defined in this way: AR r cap, A theta theta cap, A phi phi cap. curl of A is equals to 1 by r square sin theta r cap or theta cap or sin theta phi. This is very difficult to remember, but we have to. Del del r, del del theta, del del phi. AR, r times a theta, r sin theta, a phi. What about cylindrical polar? A is defined in this way. So 1 by r cap, r phi cap, z cap, del del r, del del phi, del del z, ar, r a phi, az. So gradient, divergence, curl we have written. Let's go for Laplacian. For the Cartesian coordinates, you already know del square v by del x square, del square v by del y square, del square v by del z square. This is in Cartesian. Let's write for cylindrical polar, sorry, spherical polar. 1 by r square del del r square del v del r, 1 by r square sin theta del del theta, sin theta del v del theta, 1 by r square sin square theta del square v by del phi square. This is in spherical polar. Let's write the same for cylindrical polar. 1 by r del del r, r del v del r, 1 by r square del square v by del phi square del square v by del z square. Let me give you the formula for the Dirac delta function. So the Dirac delta function is a function like this, which has value 0 everywhere except at the point x equals to 0, and if you consider the area under the curve, area will be 1. So it has a value of 0 for points other than 0 and infinity x equals to 0, and since the area under the curve is 1, so if you scan over the whole range minus infinity plus infinity, it will give you 1. Now if you consider the Dirac delta function with some offset, let's say this this is the point A, then this is delta of x minus a. Again, how do you define delta of x minus a is equals to 0? If x is not equals to a, and it is infinity if x is equals to a, and minus infinity to plus infinity delta of x minus a dx, this is equals to 1. Another formula, minus infinity plus infinity f of x delta of x minus a dx will be f of a. Some properties include delta of kx. K is some scalar 1 by modulus of k del del x, delta of minus x, delta of plus x, derivative of delta function minus delta x by x. If you take nth order derivative, you get minus 1 to the power n multiplied by n factorial delta x by x to the power n, minus infinity plus infinity delta of x minus a, x minus b dx, this is delta of a minus b, delta of, this eraser is taking too much of space. One upon 2 times modulus of a delta of x plus a delta of x minus a. If you go off for 2-dimensional Dirac delta function, how it is defined? It is delta square of xy is equals to 0 if you have x square plus y square not equals to 0, and it is infinity x square plus y square equals to 0. So in a very similar manner it is defined, and the same integration rule will be applied here. Minus infinity to plus infinity delta square dx dy is equals to 1. Some other properties include delta square ax by 1 upon modulus of ab delta square of x plus y delta square of xy can be written as the multiplication of delta x and delta y. Let's go for the three-dimensional Dirac delta function. It is written as del cube of r. As usual, you can write that as the product of delta x, delta y and delta z, and delta cube of r taken over the whole volume. It is like taking the integration from minus infinity to plus infinity for x, y and z, dx, dy, dz, and as usual it will give you 1, and the integration is taken over all space. Another similar integration we have all space delta cube. So like the one dimensional analog, we have f of r d tau. It's quite obvious, f of a. Some very important formula is there, special case. If you take divergence of r cap by r square, this gives you a result in terms of the Dirac delta function 4 pi delta cube of r. Delta cube of r is the three-dimensional Dirac delta function. Now, there is a way to represent this function delta, let's say k minus k prime. We can express it in this way: 1 upon 2 pi minus into plus infinity to the power minus I k minus k prime x prime dx prime. Okay, to get not confused, another function which looks very similar, that is called Kronecker delta. Kronecker delta, it is delta ij. It is 1 when I is equals to j. This is 0 when I not equals to j. In quantum mechanics, you must have seen it many times. Okay, Dirac delta is done. Let's go for Fourier transform formulae. Let's say we have a function h of t. We can find out the Fourier transform of that function. Fourier transform. So, Fourier transform of a function is written by h of f. This is a Fourier transform of the function, let us say h of t, e to the power minus j into 2 pi f t, or j omega t, you can also write dt. It is the Fourier transform of h of t. Now, this h of f which you have got, you can write it as in a decomposed form, real part plus this j or imaginary part. Okay, and as this is a complex quantity, you can express it in the usual way of modulus and phase. So, h of f, this is the modulus, e to the power j times theta f, this is the phase, and this modulus, you know how to evaluate it conventionally, r square plus I square. In the phase, theta f of f is given by tan inverse y by x. So, here y is this I of f and x is this r of f. And if this is the Fourier transform, inverse Fourier transform, we can also define. There are various ways to represent this Fourier transforms. Inverse Fourier transform, we will get back our function h of t minus into plus infinity h of f e to the power j 2 pi f t. Here instead of dt it will be df. Now there are some interesting Fourier transform of periodic functions. Periodic functions like cosine, sine. Let's say we are calculating the Fourier transform of cosine functions. So how does it look? If you consider a cosine function, how does it look? Let's say we are denoting it by h of t. We are writing it like a cos 2 pi f naught t. I am just showing you the visual representation. What does the Fourier transform do? So this is a cos, so there will be non-zero value here, right? So it will be like this. So this is a cosine function. If you Fourier transform, if you take the Fourier transform, what you gonna get? This will be h of f versus f. So we will get two Dirac delta function. One will be situated at f equals to f0, another will be at f equals to minus f0. Okay, this will be the peak for a by 2 delta of f plus f0, a by 2 delta of f minus f0. So Fourier transform of this function a cos 2 pi f naught t, it is a by 2 delta of f minus f naught plus delta of f plus f naught. That is why we get two Dirac delta functions. Now the same way Fourier transform of sine function. So how does a sine function look like? It will be 0 at the origin. So h of t, sine function we can represent it by a sine 2 pi f naught t. Okay, so it will be 0 like this. So on this side also you draw sinusoidal functions. So if you consider the Fourier transform, how will it look like? It will give you two peaks as usual, but they will be on the opposite side. One will be like this, another will be along this direction. This is 0, and this is f0, this is minus f0. This value is a by 2 delta of f plus f0. This is a by 2 delta f minus f0. So Fourier transform of a sine 2 pi f naught t, this is equals to minus j is a root over minus 1, a by 2 delta of f minus f naught, and that is why a minus sign is coming. The peak is in the opposite direction, and minus minus plus, so that is why f equals to minus f naught, it is on the positive side. Okay, similar functions, let's draw it. Let's say we have function like this, h of t. This is n is equals to minus infinity to plus infinity, delta of t minus n t. So at each period there will be a peak. You see, if we consider n equals to 1, the peak will appear at t, n equals to 2, peak will appear at 2t, n equals to 3, 3t, and so on. So if you draw it, how will it look like? It will look like this. Okay, so let's say we draw plotting h of t versus t. So at, let's say this is t, this is 0, this is 2t, 3t. So at each point at t, 2t, 3t will have peak, right? So this is t, this is 2t, this is 3t, and so on. And what will be the Fourier transform of this kind of functions? H of f, this will be written as 1 upon t sum over n is equals to minus infinity to plus infinity, delta of f minus n by t. So the peaks will be there, but they will be at 1 by t, 2 by t, 3 by t, and so on. So t, you see the gap is t is large. Now when the gap is 1 by t, then you see the peak will be closer to each other. I hope this is understood. So this is a plotting between h of f versus f. The peaks will be closer. At 1 by t, 2 by t, 3 by t, and so on. Now it has got similar properties that you have seen in Laplace transform. Let's say we have some scalar multiplied with the function. Let's say this is kt. Then the Fourier transform will be as usual 1 upon modulus of k, h of f upon k. Let's say h, we have some shifting t minus t naught. If you take the Fourier transform, what you gonna get? E to the power minus j 2 pi f naught. 2 pi f naught you can consider like omega h of f. Now if you want to shift the frequency shifting, e to the power j 2 pi f naught t h of t. So if you take the Fourier transform of this function, this combined function, you will get h f minus f naught. So previously if you take the Fourier transform of h of t, you get h of f, but this exponential function helps you to shift from f to f minus f naught. Okay, the same thing, let's say we are taking the Fourier transform of f of x minus a. So this will be e to the power I k a f of k. It has got various properties. Let's say modulation property. Fourier transform of f of x cos ax. So for cos, you see to Dirac delta function you have got. For this you will get half f of k plus a f of k minus a. Fourier sine transform. What is the formula for this? It is written as Fs, Fourier sine transform, 0 to infinity f of x sine kx dx, and the inverse Fourier transform, inverse Fourier sine transform, 2 by pi 0 to infinity fs of k sine kx, instead of dx will now be dk. Okay. Similarly, we have cosine, Fourier cosine transform. This erasing takes some time. Fourier cosine transform is written Fc of k, 0 to infinity f of x cos kx dx, and the inverse transform 2 by pi 0 to infinity Fc of k cos kx dk. Now, if you consider the Fourier sine transform of a double derivative and Fourier cosine transform of double derivative, what will be the result? You need to remember. Let us say if you consider the Fourier sine transform of this function del square u by del x square, this will be k times u at x is equals to 0 minus k square Fourier sine transform of u, and for the cosine transform del square u by del x square, there will be minus del u by del x equals to 0 minus k square fc, means cosine, Fourier cosine transform u. One last thing I think for this Fourier transform formula, convolution. We also discussed about the convolution theorem in Laplace transform. Here we are going for convolution theorem for Fourier transform. So, Fourier transform of convolution of two function f and g is equals to square root of 2 pi times the product of the Fourier transformed function f of k g k. And we have already defined the convolution. Convolution is defined in this way: minus infinity plus infinity f of x prime g of x minus x prime dx prime. Okay, this is a very important formula. You can directly use this. Now, let me give you some of the very important formula for Fourier transform. Let us form a table first. Here you will write the function f of t and the Fourier transform is f of omega. F of t original function and the Fourier transform is f of omega. So if you take the Fourier transform of the nth order derivative of any function f of t, Fourier transform this whole thing, it will be j omega whole to the power n into Fourier transform of omega. Remember this one, Fourier transform of f of t is f of omega. Okay, so we are writing this, the formula below based on this. If you consider the Fourier transform of f of t minus t naught, you get e to the power minus j omega t naught f of omega. So f of t e to the power j omega naught t. So this is f of omega minus omega naught. So this is a shifting property we have already discussed. So if you remember this table, then the whole Fourier series will be done, Fourier transform will be done in few minutes. You don't need to worry about other things. Now let's see f of omega. Now if you take the inverse Fourier transform of that function, then it will be 2 pi f of minus omega. So this is like reverse, you know, minus jt to the power n f of t. So nth order derivative of this function. This part is over. Let's go to the next part. F of t, f of omega, f of t, f of omega. Let's calculate the Fourier transform of delta function, which is 1 e to the power j omega naught t 2 pi delta omega minus omega naught. Signum function, it is defined as t by modulus of t 2 by j omega. J is root over minus 1. Okay, this one comes in comes multiple times in an examination. E to the power minus alpha modulus of t. This is 2 alpha by alpha square plus omega square, and this formula also comes e to the power minus t square by 2 sigma square, which is sigma root 2 pi e to the power minus sigma square omega square divided by 2. Fourier transform of 1 2 pi delta of omega. Okay, I think this is enough. Now if I give you an equation, let's say an equation, very famous equation, Maxwell's equation, let's say curl of E is equals to minus del B by del T, this equation you know. So if I take the Fourier transform on both sides, what it will produce? Let's consider let's take Fourier transform on both sides. So whenever you see this del operator, the Fourier transform will be minus jk, okay, cross E function of k So this is the Fourier transform of E, and del t it is j omega and b omega. Okay. Similarly, if I give you this equation, curl of B is equals to mu naught epsilon naught, let us say del E by del t. So for this equation, if you take the Fourier transform on both sides, so del is equals to, in place of del, the Fourier transform will be minus jk cross b, so bk mu naught epsilon naught del t, so this will be j omega and E, okay, E of k. So one thing you can remember or note, that when you have the space operator grad, after taking the Fourier transform, it will become minus jk or ik. J is the imaginary number minus root over minus 1, and for the time operator it's a del t. If you take the Fourier transform, it will be plus j omega, not minus. Okay, so if you keep these two things in mind, you can easily go for the Fourier transform. So you don't need to find out the Fourier transform in a rigorous manner, you just need to remember this formula and you can easily calculate the Fourier transform. Let us talk about basis and dimension. A set we have, let us say S, the elements are U1, U2, U3 to UN of vectors, is a basis of V if it has the following two properties. Number one, S is linearly independent. Number two, S spans V. So let's start tensors. Let's start with this element ds square equals to c square dt square minus dx square minus dy square minus dz square. So you can write it in this way: c square dt square minus dr square r square d theta square r square sin square theta d phi square. So in the tensor notation, dx0 square, dx1 square, dx2 square, dx3 square. So in shorthand notation, mu dx mu g mu nu dx. This is a matrix tensor g mu nu, which is written in this way: 1 0 0 0 0 minus 1 0 0 0 0 minus r square 0 0 0 0 minus r square sin square theta. Okay, now if you want to write it in the Cartesian coordinates, metric tensor G mu nu, you can write it 1 0 0 0 0 minus 1 0 0 0 0 minus 1 0 0 0 0 minus 1. Remember one thing, stress, strain, moment of inertia, these are second order tensor. So in tensor we need to know about contravariant tensor and covariant tensor. They are also called contravariant vector and covariant vector and mixed vector also. So contravariant vector, this contravariant vectors A prime mu, this is alpha is equals to 0 to 3 del x prime mu by del x alpha E alpha. So whenever we deal with tensors, this summation sign is ignored. Okay, you don't need to write it. So one index, so this is rank 1 contravariant matrix or contravariant tensor. If you want to write rank 2, so 2 indexes will be there. We are not writing the summation, we are just writing del x prime for mu, del x prime mu by del x alpha, del x prime nu by del x beta. Here it was, you have A alpha, so here it will be A. We have written C, so it will be C alpha beta. C alpha beta. This is contravariant tensor of rank 2. For covariant, these are similar, only the index will be below the level. Okay, not upper index, lower index will be there. So let's go for covariant vector or covariant tensor. Contra, the index are at the superscript. For covariant, it is on the subscript. Covariant vector. So if you are want to write the covariant vector of rank 1, so B prime index is at the lower subscript. Okay, we are not writing the summation. Now it is like inverse, reciprocal. Previously it was del x prime mu by del x alpha, it is del x alpha by del x prime mu, and this will be alpha will be subscript. This is rank 1. Rank 2 contravariant vector, if you want to write, you can write it in this way, C mu nu prime. So what you will write, mu del x alpha by del x prime mu del x beta del x prime nu, and C mu nu super subscript, so alpha beta at the subscript. This is the covariant vector of rank 2. Now if one index is at the superscript and another on the subs, then that is called a mixed tensor or mixed vector. Let's say mixed tensor. Mixed tensor means you have subscript and superscript both. So for superscript, you know, you have to write del x prime mu by del x alpha. For subscript, you have to write that del x beta first, del x prime nu. C alpha will be above, beta will be below. Okay, so this is a mixed tensor of rank 2. 2 indices, 2 rank. Now there is something called contraction of a tensor. Okay. Now there are multiple. This is a mixed tensor actually. Contraction means if two of the indices are equal. So let's first write it as usual. Mu nu is at the superscript. So what we will write, del x prime mu by del x alpha, del x prime nu by del x beta, let's say. Now this alpha and beta. So alpha beta we cannot write. Okay. We need to use some other symbol because alpha beta is already there. So instead of alpha beta, we can just write, let's say, rho lambda and gamma and delta. So rho lambda superscript, gamma delta subscript. Okay, this is a mixed tensor of rank 4. Now contraction of a tensor means when the indices becomes equal. Now we equate the contravariant index nu, let's say, to the covariant index alpha. Then we can write C prime mu beta. So once you equate them, nu and alpha, then these two terms will get cancelled. So what you will have, del x prime mu by del x rho del x delta by del x prime beta. Okay, these two terms in between get cancelled because they are equal, you have equated them. T rho lambda, lambda and delta become equal, so lambda delta. So this is effectively del x prime mu by del x rho del x delta by del x prime beta T rho delta. So previously 4 indices were there, but now it is 2. So we have contracted. So this is the contraction of a tensor. Now how do we define rank? I hope you have understood what is rank. Rank is the total number of contravariant and covariant indices of a tensor. So let me reiterate it again. Rank of a tensor is defined as the total number of contravariant and covariant indices of a tensor. Now let's say object versus the rank. Whatever scalar we have, any number and all those things, the scalars are tensors of rank 0, vectors are tensors of rank 1, n cross n matrix, these are tensor of rank 2, and in general For higher order, high rank tensors are called tensors. So tensor is a general term. Scalar, vector, matrices, these are all tensors of different ranks. Now for tensors there are a number of independent components. Okay, so there is some formula. The number of independent components of a totally symmetric matrix, symmetric tensor, matrix or tensor, whatever you say. It is given by D plus R minus 1 C R. R is rank, D is the dimension. What dimension you are considering? Now same for antisymmetric matrix. The formula will be DCR. Dimension D means each index runs from 1 to D. So you can also write a note if you forget. Dimension D means each index runs from 1 to D. A similar related thing is there, Levi-Civita symbol. Let's complete that. It will not take much time. Let's complete Levi-Civita symbol. Levi-Civita symbol. So let's first define it in 3D. Levi-Civita symbol epsilon I j k. It is plus 1. If you consider the even combination permutation of x, y and j, I j k is equals to plus 1 when I j k is an even permutation. X, Y, Z, and it is minus 1 if I j k is an odd permutation. And 0 if any two indices are equal. Okay, we will define with you can make a series like this. So epsilon 1, 2, 3 or epsilon 2 3 1, 3 1 2, they all will be 1. Okay. On the other hand, if you consider 1 3 2, 3 2 1, 2 1 3, this will be -1. Another combination, like if you consider 1 1 2, 2 2 3, 1 2 2, all of them will be 0 because repetition of index. Go for 2D. Epsilon ij plus 1 if ij 1 2, minus 1 ij 2 1 0, ij are equal. So how many components you can get? You can either get epsilon 1 1, 1 2, 2 1, 2 2. So you can also express it in the form of matrix 1 1 2 2. So they are equal 1 2 1, 2 1 minus 1. Now there is some important relation here. Two-dimensional Lewis-Leavitt symbol, epsilon ij, epsilon mn. You can write it in terms of the Kronecker delta. Delta mi, you see mi delta nj minus delta m. Now you take the other pair mj delta ni. Okay. Now if you consider ijk imn, then what will you write? Mi is same, so you will have m and j, n and k minus the m and k, n and j. So sometimes you need to use this formula. Now you can write the determinant of a matrix in terms of the Lewis-Leavitt symbol. Let's say we have a matrix A whose elements are aij, then you can write the determinant of this matrix A in terms of the Lewis-Leavitt symbol by using this 1 2 3. So this is where the Lewis-Leavitt symbol holds its importance. We can write many extended expression in a very short hand notation by using this Lewis-Leavitt symbol. Epsilon ijk a1 I a2j a3k. You can also express the cross product of two vectors in terms of the Lewis-Leavitt symbol. Let's say we have two vectors, one vector is a, its components being a1 a2 a3, another vectors b we have its components being b1 b2 b3. Now if you take the cross product between these two vectors, you can express it the usual way. First write e1 e2 e3, these are the unit vectors along xyz axis, a1 a2 a3 b1 b2 b3. This is the usual way we write. You can express it in terms of the Lewis-Leavitt symbol by this expression: I is equals to 1 to 3, j is equals to 1 to 3, k is equals to 1 to 3, epsilon I j k ei cap dot a j b k. For example, if you take the ith component, you can write it ith component, jth component, kth component, I equals to 1 2 3, so x y z. So if I want to write, let's say, the ith component, what you get? e1 a2 b3 minus a3 b2, you get, right? Now using this formula also you will get it. Let's write the ith component. Ith component, you can write A cross B. Its ith component becomes epsilon I j k A j b k, and that is why A cross B, if you write the first component epsilon 1 2 3 A2 B3 plus epsilon 1 3 2 A3 B2. Epsilon 1 3 1 to 3 is 1, and epsilon 1 3 2 is minus 1. This is how we can write. We can also write the scalar triple product A dot B cross C. This is a scalar triple product. We can also express it in terms of a Levi-Civita symbol epsilon I j k AI Bj Ck. We are almost at the end. One thing is left, that is special function. Let me just give you the formula sheet for special function. So we have 4 special functions. Let's write them in the form of a table. So we will have 4 things: name of the special function, differential equation, generating function, and the orthogonality relation. These are the things you need to remember. First, we will go for Bessel. You know the differential equation x square d square y by dx square x dy dx x square minus n square into y is equals to 0. What is the generating function for this? E to the power x by 2 z minus 1 by z. This is equals to n is equals to minus infinity to plus infinity z to the power n jn of x. What about the orthogonality? 0 to 1 x jn alpha x jn beta x dx. This is equals to half jn plus 1 alpha whole square when we have alpha is equals to beta, and is equals to 0 when alpha not equals to beta. Again, function, differential equation, generating function, and orthogonality. So Bessel is done. Let's go for Legendre. The differential equation 1 minus x square d square y by dx square minus 2x dy dx plus n into n plus 1 y equals to 0. Generating function will be 1 minus 2x t plus t square to the power minus half equals to n is equals to 0 to infinity Pn of x t to the power n. X lies between plus minus 1, t is less than 1, orthogonality minus 1 to 1, Pnx Pm of x dx, this is equals to 0, m not equals to n, this is equals to 2 by 2n plus 1 when m is equals to n. So legendary is done. Let's go for Hermite. Differential equation d square y by dx square minus 2x dy by dx plus 2ny is equals to 0. A to the power 2x t minus t square n equals to 0 to infinity hn of x t to the power n by n factorial. It is minus infinity to plus infinity. This is very important. A to the minus x square hmx hnx dx. When m not equals to n, it is 0, and when m is equals to n, 2 to the power n n factorial root pi. Last one, log here. The differential equation x times d square y by dx square plus 1 minus x dy by dx plus ny is equals to 0. Generating function 1 by 1 minus t a to the power minus xt by 1 minus t, n is equals to 0 to infinity log r functions t to the power n by n factorial, orthogonality 0 to infinity e power minus x ln of x tx. It is 0 when m not equals to n, and when m is equals to n, this is n factorial square. So finally we have covered the entire short notes on mathematical physics. So it is taking huge time, guys. It is not possible to cover all the subjects in one day. We have to take 10 days, 10 separate videos to cover the whole. Okay, in the upcoming future we'll be bringing for other subjects as well. Mathematics in itself is very huge, but still we have completed today.